Hi. Today I will be telling you about some research that I've been doing with my student, Murtaza Motiwala, and another professor at Georgia Tech, Santosh Vempala, who directs the Algorithms and Randomness Center. This work that I'm going to describe is basically a very scalable way of exposing lots and lots of diverse paths to end systems. So as we know, there are several things that routing actually does quite well these days, providing reachability to lots and lots of destinations, and doing so in a scalable fashion, handling things like churn and size of the global total number of networks and destinations quite well. There are other things that arguably it does less well. I guess even the first two are scalability in particular is coming into debate of recently as well. But these second two goals, diversity in particular, is something that arguably today's protocols don't do quite as well. In particular, what we mean by this is can we expose paths to end hosts in such a way that if nodes and links fail, for some definition of fail, that could be hard failures, but it could also be things like persistent congestion or packet loss. Can we maintain connectivity, good connectivity between the endpoints? That might be useful for a variety of reasons. One, of course, being fault tolerance. The other, of course, being if you could have these multiple paths available so that the end host could use them, say, simultaneously, then you might have the ability to exploit better the capacity of the underlying network. Imagine if you could use multiple paths in parallel rather than just a single path. The other, of course, is that you want to do this in such a way that if you're using these paths that are, rather than just the single shortest path or the single best path, you're going to, of course, by nature, be picking some paths that are, not the absolute best, but the set of paths that you use, you want to, they shouldn't be too circuitous or too long. In the case of shortest paths routing, we like to think of this as having low stretch. Arguably, we'd like to do a little better than what today's routing protocols, in particular today's IGPs, are giving us. Most of this talk is going to be about sort of IGP style routing and how we could do better. One particular approach to doing this might be doing something like multipath, and of course there are existing solutions out there today, like ECMP and things like that we know about, that do allow nodes to send traffic along multiple paths through the network. Now, sort of vanilla multipath, though, has its own set of problems, right? So imagine, this is just a toy example, of course, but just to illustrate the point clearly. Suppose that we have, two link disjoint paths between a node S and a node T, a red path and a blue path. Well, that's all well and good, but the problem here is, of course, that if any link on each of these paths fails, then S and T become disconnected, right? Doesn't have to be a cut of the graph. Just any link failing on both of these paths at once creates problems by disconnecting S from T. Again, by failure here, we could mean cut, or we could also just be talking about poor performance, congestion. What we'd really like is something more like this, where the end systems, or any pair of nodes, if you will, remain connected unless the underlying graph itself is disconnected, right? So if we have a cut, for example, as I've shown here, if the red edge and the blue edge that I've shown failing here, that actually creates a partition in the graph. Well, there's obviously nothing we can do in that case. But in the former case, where the underlying graph, the physical topology is still connected, we want the routing protocol actually to give us some way, or give S some way of actually reaching T, and that's basically what splicing is all about. Splicing is actually not a new routing protocol at all. What we're going to do is take the IGP and play some tricks with it, actually run it multiple times. So there's some support for similar types of things in routers today. There are a few tweaks that I think that we might need to actually make this happen. So I've got some questions for you at the end about that. The main idea is actually to run multiple instances of your routing protocol, right? So you're going to compute multiple forwarding trees per destination, essentially. How are you going to do that? Well, you're basically going to run multiple instances of the protocol, but each instance is going to be configured slightly different way. So if you're familiar with some things in the IETF like multi-topology routing, or there's some recent work on multi-routing configuration, it's a similar. Those are similar kinds of ideas. Now, the trick here that we're going to use that gives us a big win over those existing schemes is we're going to allow the packets to actually switch trees anywhere midstream along en route from source to destination. Right? So imagine we have a graph like this from S to T, and the first step, of course, is, as I mentioned, we're going to run multiple instances of the routing protocol, essentially by, and then for each instance, we're going to run those with perturbed link weights of the base graph. Okay, so suppose we have now a red tree and a green tree from S to T. And the second step, of course, is rather than just picking the red tree or the green tree, we're going to allow that traffic to actually switch from red to green at any point along the path. You may have some questions about this. In particular, does it cause loops? And in the interest of time, I'm not going to get into that in the talk, but if you want to talk about it in the questions, we can certainly get into that. So that's basically the main idea. And the reason I think this is sort of particularly interesting is you note that by allowing the traffic to switch at any point along the path, essentially you get an exponential number of choices in terms of the paths that you can use to send your traffic from S to T, but you don't get an exponential increase in complexity, right? So the sort of Achilles heel of a lot of multipath routing protocols is, yes, you can advertise multiple paths out, but is every node going to advertise multiple paths? And that could create a lot of state and churn and so forth. And we don't really run into any of those problems. All we're doing is running k instances of the routing protocol. So it's a linear increase in the amount of state, but we get an exponential gain in terms of the number of paths that are available to the source. So how do we do this? Let me sort of describe each of those steps in sequence. So the first is the first thing we need to do is give each instance of the routing protocol access to different paths in the underlying graph. And the idea is basically this. Imagine you start off with a base graph in your IGP, right, that has certain link weights. So the link weights that I haven't labeled there, you can just assume they're 1. So this graph, there's some shortest path tree that is formed from S to T. And the idea is take that base graph and perturb the link weights. Right, and there are various ways to perturb them. There's a tech report that I'll point you to at the end of the talk where we look at different types of perturbation schemes. But the idea is then take those link weights and generate a new set of weights based on perturbations of the original. So they're not completely random, but you take the base graph and actually just tweak the weights just slightly. So what you get are paths that are slightly longer than shortest paths, and I'll briefly describe what I mean by slightly longer in a little bit. But the idea is if you do this repeatedly, then you get a bunch of perturbed graphs and you can overlay them, and now you have a bunch of graphs like the red tree and the green tree, et cetera, like I showed you on the previous slide. So that's kind of the first step, is run the routing protocol multiple times to get multiple trees. The next step is actually to allow these tables to actually coexist. And this actually, there's similar type of functionality that's already in routers today with VRFs and such. But the idea here is now just to install those in separate forwarding tables and index them based on some, we call it sort of a slice ID. Then there's one additional thing that actually has to be added, to actually exercise these paths that are sitting there, right? And that's that we need to actually indicate somewhere at each hop which forwarding table this packet should actually take at that particular node. So what we do is actually toss an extra header. This could presumably go in an IP option field, or in the paper we describe it as just adding a shim right underneath the IP header. But the idea is basically you just have a string of bits, and at each hop, suppose you have k of these trees, right? So then you're going to need log k bits to actually index into each of those forwarding tables, right? So now the operation that each router is going to perform, or each router that supports this, is that it's going to look at the rightmost log k bits, figure out which table it should index into, use that particular next hop to forward the traffic, shift the bits and forward the packet. There are a couple things I want to draw your attention to. The first is that based on where we decide to put these bits, this is totally incrementally deployable because any router that doesn't understand this can just forward the traffic based on the IP header. Any router that does can do this magic. The other is which may raise concern. I guess we can talk about that at the end as well. This is a research talk. Is that to access these multiple paths, the source doesn't need to do anything fancy like know the IP addresses of the hops along the path. Basically, this sequence of bits is opaque, so it gets this sort of nice black box interface where all it needs to do is say change these bits, and with high probability it will get a new path. Or suppose it wants to use multiple paths in parallel, it can send traffic out to some destination with different bits set in this header and send traffic along multiple paths in parallel. How well does this work? That's a good question. We're actually still trying to figure that out. But we have some preliminary results. This is actually where also you folks could help us in sort of understanding what topologies look like better, because we don't have a whole lot of real topologies that we can test this on. But we did do this on the Géant topology, which I think was mentioned in a couple talks ago. We have access to that topology. And there's a research tool called Rocket Fuel, which I think maybe those folks came here several nanogs ago and talked about, their best guesses of ISP topologies. So, for all their faults, that's the best we have. So we use one of those as well to try this. Then we basically ran this a bunch of times. We ran a bunch of trials, and what we did is see if we removed edges from each of these topologies with a certain probability, that basically gives us a probability of disconnection of both in the underlying graph and in whatever we decide to put on top of it, right? So these lines are a little thin. So let me sort of point with the arrow here. So on the x-axis, basically, this is the probability of any particular link in the topology failing. So this is, we basically flip a weighted coin and decide whether or not to remove each edge, and that gives us now the topology with the failures injected. And then what we're asking on the y-axis here is what are the fraction of source-destination pairs that actually become disconnected as a result of this. So ideally, what you'd like to see in this graph is some line that basically goes pretty much along the bottom here, until the probability of failure of each link failing gets really high, and then lots of things start to become disconnected. So two things to note. One is this black dotted line. That's this characteristic for the underlying graph itself, right? So that's before we run any routing protocols on top of it at all. We can ask, do source-destination pairs get disconnected in the underlying graph itself? What are the properties of the physical graph? So that's the best we could do. This thick red line up here on top is for k equals 1. So that's basically one instance of shortest path. So that's basically, this is what you would get if you ran just, your IGP. What we see, and actually the best way to see this is actually to zoom in a little bit here. We look at these sort of low probability of failures, and you can see for actually just a very small number of slices, k equals 4 or 5, we're really approaching, about as best you can do. That is the reliability that we're seeing in terms of do these pairs actually remain connected. It's actually approaching the reliability that you actually get in the underlying physical graph. So that's pretty nice. Now the cost, of course, as I mentioned, is that because we're perturbing the link weights, some of these paths are actually slightly longer. So you might ask how long. That depends on how you perturb the link weights. But for this particular experiment, it was about 30% longer. Okay. So that's basically just a simulation as far as, we can run these, run this on top of the graph and ask what kind of properties we get. There are, of course, a bunch of open questions as far as, can you react fast enough, et cetera, et cetera. So we're actually trying to build a prototype of this as well. Actually be interested to hear from router vendors and things like that to see how much of a leap this would take to actually, put this kind of functionality in a router. But there is a prototype implementation going on a network testbed called Vinny, and I won't get into the details, but the details are in the slides themselves. So There are, of course, a bunch of open questions that we're trying to answer. And hopefully at some point I'll come back with some good answers on this. One, of course, is the dynamics themselves. Can end hosts and end systems react fast enough to recover from these failures? How do you find actually an alternate path that works? There are related questions, of course, which is that if you squint, this kind of looks like source routing. So is this really going to frustrate? Is the uncertainty of the traffic that's offered to a network going to frustrate operators? I guess that's a question I have for you. We'd really like to try this out on other topologies. So I realize the sensitivity of the data here, but if this is something that any particular ISP finds interesting, we'd definitely like to hear more from you and perhaps work together on that. So I guess the meta question there is this interesting? And a question I have for vendors and router vendors would be, how big of a jump is this today? Of course, there are certain things already, as I mentioned, that are there, but things like indexing, using the bits to index into different forwarding tables at each hop might be something that we'd have to add. There's a slight variation of this. How much time do I have? 2 minutes, perfect. So there's a slight variation of this that we're also thinking about. We call this BGP splicing. So the idea here, this is just a one-slide summary of this idea, but the idea here is rather than running multiple routing protocols, exploit the fact that the RIB itself actually has multiple alternate paths or alternate routes in the RIB. And if you could somehow push those down into the forwarding table, could you use these routing bits to actually do the same kind of thing, like switch at ingress or egress? The BGP route that's being used to send traffic to a particular destination. Of course, this I think requires a bit more thought and perhaps considerable changes. There's a bunch of related work which I'm going to cruise through, but you have the slides as well. Most related work I think is this first group of work, which is sort of there's been a lot of work on pre-computing backup paths, obviously, and in particular that in the IETF on multi-topology routing, et cetera. We think this scheme has quite a lot to offer. It's quite simple, right? There's no complexity as far as needing to specify IP addresses of routers or do any source routing-ish types of things. The bits are enough to provide access to different paths through the network, and as I mentioned, it doesn't matter if a particular router does or doesn't understand it. Those that do can actually allow the end host to exploit this diversity. As I mentioned before, you get this nice exponential increase in the number of paths that are available for just a linear increase in state. The other thing which we're exploring too is that this does beg the question of how fast you need the routing protocols to actually converge, right? Because if you have an end host that can, or an end system of some kind that can detect that the network isn't performing well for whatever reason, hard failure, congestion, packet loss, et cetera, and somehow route around that, then that begs the question of how fast you actually need the routing protocol to detect maybe only a subset of these problems. And the other thing, of course, is that you notice I didn't actually propose any real changes to the routing protocols themselves, just running multiple instances of existing protocols. So that actually has a corollary, which is that this could apply to all types of routing. I mean, I described it in terms of IGP and a little bit in terms of BGP, but certainly other types of routing protocols to overlay type routing, et cetera, would certainly apply. So we have a lot of ideas for how this might apply. We'd certainly welcome your suggestions as well, and there is a tech report there which I hope that some folks will check out, and I'm curious to hear from folks about their reaction to this. Thanks.
Okay, thank you, Nick.